Okay, I hit record, and that's gonna make sure that everybody has a copy of this afterwards. We've got maybe 2/3 of our participants here. So I'm going to go ahead and get started with some of our administrative tasks, and then to get started introducing our speaker. So I would like to welcome everyone to another of our ISNR webinars. And if you haven't been here before, to give you a little bit of orientation to how we do this, we keep everyone muted throughout the length of the webinar. And that's just so that we can get through the many slides being presented to us. However, at any time during the talk, I'd like to welcome you to either in the chat window, or there's a question and answer bar below. If you have questions for our guest, please to go ahead and type those in. If it seems to be a critical question, then I will interrupt. Otherwise, we're going to try to save those to the last 5 minutes. If we have many questions, and if our speaker is available, it's a little late where he is right now, we'll go over. Last time we I think went an additional 15-20 minutes over, and it's really up to our participants and our guest speaker how long we keep the tape rolling. The question comes up, can you have a copy of the slides and the video? Absolutely, yes, we send out the videos usually on the Tuesday after the talks, and it's the choice of our speaker whether or not to make the slides available. And our guest today is going to provide us with a copy of this. Also, a few data files that if you have a WinEEG, which will be part of the demo that we're going to see, that you can play with some of these analysis techniques yourself. So slides, yes, video, yes. And finally, how do you get your CEs? Well, you look for the link in the email receipt that you received from R. Cassidy. But again, please give us until about Tuesday to get the attendee list over to that granting organization. And please also remember that you need to stay for the entire talk to receive your credits. So with all that housekeeping now cleared up, I would like to introduce our guest for today. Professor Kropotov is head of the laboratory at the Institute of Human Brain of the Russian Academy of Sciences. He's the author of 300 scientific papers and 13 books. He received the USSR State Prize in 1985 and the Copernicus Prize in 2009. His current scientific research focuses on functional neuromarkers for psychiatry and neurology. And thank you very much for being with us today, Professor. We're looking forward to your talk.
Thank you. Thank you very much for introduction. So I'm going to talk about advantages and limitations of independent component analysis, and that I'm going to share with you. So, and I start with the cocktail party phenomenon. When there are many people in the room, and each of them is talking, and there are several microphones in the room, and each microphone picks up a mixture of acoustic signals, and having this recording from this microphone, the problem is how to find out who said what. This is a kind of a problem for KGB to know who is saying what. And this is in science is a general problem, and we call it blind source separation problem. And blind source separation, by definition, is the separation of a set of signals from the mixture of these signals without the aid of information about the source signals or mixing processes. And this blind source separation relies on the assumption that the source signals are not related to each other. That means that knowing something about one source, you cannot say anything about the other source. And in general, the method of blind source separation differ according to the definition of what is not related. And for example, the signals may be considered as statistically independent. This is one model, and the ICA uses this model.
Just now starting, okay?
Okay.
Or
Showing webinar in progress. Perfect.
Are you in?
or to be mutually decorrelated, such as second order statistic methods. When we talk about ICA, the ICA finds independent component by maximizing the statistical independence of the estimated component. And there are many ways how you can use ICA, and there are two broad definitions of independence. One is a minimization of mutual information. The other is a maximization of non-Gaussianity. And here in this talk, I'm going to talk about Infomax algorithm that is used in one of the ICA methods. And I usually show this picture to demonstrate the basic idea behind this method. So here I present the kind of a picture of the brain, mostly cortical areas. And there are many generators of the currents, of the local currents in different parts of the cortex. And this generator, they induce currents, and currents in their turn induce potentials that can be recorded by electrodes placed on the skull. And each of these sources generate a potential at each of the electrodes with certain weights. And the goal of the methodology we are talking about is to extract sources, these hidden sources, from a recording of the potentials. So consider that X are potentials that are recorded in different electrodes. S are the unknown sources, and A are the weights from which these sources produce potentials of the electrons. And so the matrix A, actually the columns of matrix A represent topographies of the hidden sources. And basically the goal is to find a mixing matrix and the sources. And the sources can be found as a product of the unmixing matrix, which can be considered as the inverse matrix of the mixing matrix, and X. So it is simple like this. This and all mathematical operations are actually linear. And this picture always is shown to demonstrate the ICA, the method of ICA. So X1, X2 are what we record, and S1, S2 are the sources of in this case, of potentials. Okay, and so the idea is to find linear combination of X1 and X2 to fit this S1 and S2 sources. And the first I have to say that this method was applied for EEG, for spontaneous EEG, by Scott McKay quite a long time ago. So it looked like that 24 years from now. Okay, so again, I am talking very common thing, but I think that people they want to know from different sources about this. So how it works? Okay, so suppose you have two different people, source one and source two, that are talking independently, of course, of each other. We have two microphones, and the microphone, each of microphone is registers the acoustic signal, which is a sum of two different voices. So the question is, when you have recording from this microphone, having them, can you applying ICA restore the sources? And that is the question, yes, it works. And this picture is to demonstrate what does it mean to be mutually independent. And this picture on the top shows two voices, one voice, another voice. And at the bottom, there is a raster and a kind of the picture X. One voice is vertical line, the other voice is horizontal line. And this is a kind of scatterogram, and this scatterogram actually demonstrates what we call mutual independence. So they are indeed, these two voices are mutually independent. But if you record these voices from microphone, and each microphone actually record a sum of voices with different weights, then you get the picture that in the bottom to the right. And quite clear, you see that in this case, in the case of the mixtures, they are not mutually independent. They correlate with each other. And basically the idea is from the situation when we have this quite clear cross correlation to get the picture of mutually independent components. So we need somehow to get the ways in which these linear combinations can give this mutual independence. And basically, to be used, the ICA is based on some presumptions. So one of the presumptions is that the signals here, the signals that we're looking for must be stationary, stationary non-Gaussian operations. But when we work with event-related potential, this is not the case. Event-related potentials, they are, by definition, they are not stationary. And we need to use a different approach. And one of them that we are using in our laboratory is a joint diagonalization of cross-variance matrices. The first paper on this topic was published by us in 2013, 7 years ago. Okay, so what are ICA assumptions for EEG time series? First of all, signal conduction times from the sources are equal. And the summation of those currents at the scalp sensors is linear. And these two suggestions are quite reasonable assumptions for the currents carried out to the scalp electrodes by volume conductance, of course, at EEG frequencies. So basically, this is a correct assumption. Then the second, spatial projections of components are fixed across time. Well, if we are talking about, say, eye movement artifact, eyes are quite stable, and the special projections of the eye movement components are fixed. across time. There is no problem. Then source activation are temporarily independent on one another across the input data. So basically, this is also a correct assumption because when we are talking about eye movement artifact, they usually occur independently of the spontaneous EEG. And the next assumption is that the statistical distribution of component activation values are not Gaussian. If you look at the oculogram, you can see that the distribution of the oculogram values are not Gaussian. So, and also some of the EEG component, they're sinusoidal, and sinusoidal distribution is not Gaussian. Okay, there are several packages in the software that are using ICA method, and in the field of event-related potential, this is a standard procedure. And we wrote more than 100 papers on event-related potentials. In all of these papers, we used independent component analysis for correction eye movement artifact. And there are several software packages that are using ICA. And of course, one of them is the EEG lab that was actually developed by Delorme and McCake. I don't know how to produce it correctly, Delorme or Delorme. But anyway, they are quite famous people who actually introduced the ICA to EEG research. And this software package actually runs under MATLAB. And of course, WinEEG, our software, the software that was developed in our laboratory and is now commercially available. And also this software uses HBI database to compare EEG spectra, spontaneous EEG with the database, and also event-related potentials with the database. Okay, so here I present eye movement artifacts, so a simple EEG recorded in a healthy subject. These are electrodes, 19 electrodes. X-axis is time, of course, and you have to remember that eyes, the balls of the eyes, are actually clear electrical dipole that are positively charged at the, they are negatively charged at the retina and positively charged at the cornea. So, and when we blink, the eyes automatically go up. And because of that, this dipole, electrical dipole, positive electrical dipole hits FP1, FP2 electrodes. It generates the topography, which is shown at the bottom of this slide on the left. At the bottom of the left, I demonstrate the topography of eye blink. And quite often people also make artifact or lateral eye movement, saccadic eye movement. And here at the bottom to the right, I demonstrate the topography, the map of lateral eye movement. So quite clear topography is quite different topography for eye blink and lateral eye movement. And the question is how we can actually extract them in EEG, how we are going to get rid of them. This is done by ICA method, and this is demonstrated by this slide. To the left, you see the EEG recorded in a healthy subject. This is actually was my younger son. And the referential montage, then we apply ICA to 3 minutes of EEG, spontaneous EEG in nice open condition. And we got the following component. Each component, of course, is characterized by topography. Remember the columns of the mixing matrix. So the topography and the time dynamic, and you can compute EEG spectra of this time dynamic. On the right, you can see EEG spectra of the corresponding component. Quite clear, you see eye blink topography, eye blink dynamic, eye blink spectra. The topography of widely distributed component and its time dynamic, the parietal alpha rhythm component, quite clear peak in alpha frequency band. The frontal midline theta rhythm component with a quite clear peak at about 6 Hertz and located frontally is frontal midline theta rhythm component. And in this case, another artifact, which is called cardioballistic artifact. Remember when you place electrodes on the artery on the head, and the artery is pulsating, so each pulsation is presented as artifact in this EEG recording. So basically you have this component, which again are a mixture of the initial potential of the electrodes. And basically you can delete one of these components to get rid of the corresponding corresponding artifact. Just simply delete the corresponding component. And when you do it, you get something like this. So this is the EEG with eye blink artifact. By the way, the EEG is common average montage, and you apply ICA, and you don't see any artifact with eye blinks. Then in 2014, we actually applied this ICA on a big collection of 3 minutes 9-channel EEG record of about 400 healthy adults in different conditions. Here I present eyes open condition, and you can see the topographies of independent components that were extracted. And you can see that there are 18 relatively local component, and the one global component that integrate quite widely distributed sources. The nature of this global component is not clear. One possible explanation is that it reflects activity of the reference electrodes, which I doubt. The other possible explanation is that the global component reflects a general source located maybe in the brainstem, which drives activity in those widely distributed areas, a kind of a common source. And that is why I prefer to get rid of the common source when I analyze spontaneous EEG. Remember that there are many montages, the way how you can look at EEG. One of them is referential montage, and you can place this reference montage either on the linked ears or the linked mastoid, on the tip of the nose. and an EEG depends very much on the way how you selected the reference. There is also a common average montage, and the reason for that is presenting here why it works quite nicely. And of course, there are local average montage like Laplacian montages, like current source density montages, etc., etc., etc. Okay, and I have to tell you that although the EEG is a conventional method in ERP research, for some reason in the field of quantitative EEG, in the group of people who are working with EEG spectrum, with EEG coherence, and they try to, on the basis of this EEG analysis, they try to suggest different types of neurofeedback protocol. For in this group, there is the ICA actually meets with some question, and the basic question that this group raises is, does removing ICA artifact components in EEG correct its phase? Okay, and here I present the a kind of the site of the Schwartz Center for Computational Neuroscience, and this is presented by Arnaud Delarme, and well, the answer to the question is actually no. And this site, you can go to the site and look at the argument that they present. And those are people who actually respect very much. And Arnaud is the developer of EEG Lab. And Roberto Pasquale Marquis is the developer of Loretta, is also is also saying that the answer should be no. And one of the reasons for that is quite simple. And I'm going to demonstrate it. I mean that I prepared an EEG, and I'm going to demonstrate it using our software. So one of the reasons why the answer is no is that when you are using ICA for correcting for artifact, we are using this method is a linear combination, and the making a linear subtraction, linear mathematical computations, you simply cannot change, by definition, you cannot change the phase of the EEG signal. And I'm going to demonstrate it. So I prepared, and I think that's what I prepared in terms of slides. And now I'm going to start WinEEG software. This is WinEEG software. That's the software that we developed in our laboratory. This is EEG, as you can see, in a subject with autistic spectrum disorder. And I'm going to analyze this EEG using ICA methods, and I will show you the advantages and of course you will see the disadvantages of this methodology. Okay, so look. First of all, let us change the montage. I prefer using the common average montage, although it does not really matter, but for didactic purposes, at least you need somehow to select the montage. I select the common average montage. Okay, the first step. Then the next step, let us select some time interval for which we are going to apply independent component analysis. Okay, say I select, say, 175 seconds. I think it will be enough for applying ICA. Then let us do that. Let us select some fragment. Before doing any analysis, let us select some fragment, okay, and of EEG, and let me color this fragment by, say, the color could be red. So red is EEG recorded in this particular subject in common average montage before doing any artifact correction. Okay, so copy, and I open some okay, so this is green, red is EEG recorded in this particular subject, the one of the fragments of EEG, okay? Then I'm going to apply ICA to this quite long, more than 2 minutes EEG interval. So I go, of course, to analysis, and I use the procedure with the called artifact correction procedure. So on the left, you see the raw EEG, and I'm using, although some people they like to use PCI, and this option can be used in our software, but I'm here to demonstrate the ICA method. So I run independent component analysis and then just wait. It's iteration procedure. It takes some time. And after some time, you can see what happened, okay? I think that I will get rid. Okay, so you see this is on the left, this is a raw EEG. On the right, these are topographies of EEG components. So we run ICA on this EEG fragment. And this component, the pictures, they show the relative EEG power of this component. The highest EEG power is generated by this component, it's I-blink component. And remember, I showed to you that this is I-blink, and the second one is a lateral eye movement component. I select both of them, and they simply extracted from from EEG. And on the left, you see the raw EEG. Then the next column is corrected EEG. These are excluded artifacts. You see artifact of eye blink, artifact of lateral eye movement here. And that's it. And I click OK. Okay, now we got rid of this artifact. And let us make the color of these waveforms as, say, green, blue. Okay, blue is the color. Okay, and we copy the same fragment. I copy the same fragment. This is the EEG, and I copy and I make the. Now you can see the green, the red is initial EEG fragment without any artifact correction. And the blue is artifact correction procedure after artifact correction procedure with, and basically you can see, yes, indeed, eye blinks, the eye blinks artifact like here. It's actually, we get rid of this artifact. But the EEG signals, as you can see, they remain the same. Look, here, even here, at the P2 electrodes, you see this oscillation in theta frequency band. They're quite clear. They are the same. There is no distortion on phase. Okay, so I think that it's actually quite clear that ICA do not produce any distortion in EEG, in spontaneous EEG phase. Now, let me demonstrate what else can we do with this EEG recorded in autistic spectrum disorder children, and how we can use the database and the independent component analysis to actually to try to figure out why this particular patient having symptoms of autistic spectrum disorder. So coming back to the EEG, restore the color. I actually prefer the black color, not green, not red, not white. So the waveforms, black color. Okay, so, and we corrected using ICA. Okay, and by the way, if you look more carefully at the EEG, that you can see from time to time, you see that at T4 electrodes, there are spike slow wave complexes. You see these spikes, especially at the end. I'm going to you see, these are spikes. These are spikes, and quite clear that something happens, and there is a focus in this part of the cortex. Okay, how we are going to deal with this? Okay, so I'm going to, first of all, to learn where this focus is located. And the first thing I'm going to do, I'm going first of all to actually to find and to detect these spikes. So I go to analysis, and I use the option from menu spike detection, automatic spike detection. This is the parameters that actually derived from our database. In our database, we have about 1,000 EEG recorded in patients with epilepsy. And on the basis of this data, we just computed, extracted these parameters, nothing special, and I click OK. And you see these components, these spikes, they were marked automatically. I go to another option. I want to average those spikes for all EEG fragment. This, and remember the spike was at T4 electrodes. And this is the average spikes. And if you look at the numbers, so at T5, the number of automatically recorded spike is 106. And some artificial spikes were also found at FP2 electrodes, but the number is 4. So they're not real spikes. Anyway, so this is we can actually map topography. I think it's very important to know the topography of this spike. Okay. This is a topography. Just remember that this is topography of the spike. Here I present the dipole, and the spike can be modeled by a single dipole. And here, as you can see, if I place the relative residual energy of this dipole approximation is very small, is 0.04. So it's quite nice dipole approximation. And, but, okay, so we quite clearly see this in this spike detection procedure. I actually can try to find where this this focus is localized using Loretta, and also we are now using standardized Loretta. I'm using this standardized Loretta, and this standardized Loretta gives us the source, which is actually localized in Broadman area 6 in precentral gyrus. So it's this is actually so-called Rolandic spike. So this is a spike that is located in the Rolandic tissue on the right side. This is a Rolandic spike. And we know that in a patient with autistic spectrum disorder, we see quite often abnormal EEG, including this Rolandic spike. The focus is near the Rolandic tissue, and from our experience, I mean that experience of our laboratory and from literature, we know that having spike, even if you don't have any epilepsy, is actually disrupts normal information processing in this area, and quite often it's either associated with symptoms of attention deficit or even with the symptoms of autistic spectrum disorder. So we know that there is a focus in the cortex, and we know that it can produce even autistic spectrum disorder symptoms in particular subjects. So the first thing you have to do is just to consider working on the focus. One way, of course, could be using, you know, you are neuropractitioners, you are using different kind of neurofeedback protocols. And one of them could be actually training in this particular area at T4 new rhythm up The other way using transcranial direct current stimulation and using cathodal stimulation, so you place cathode at one area and anode at the other area of this dipole. So you try to inhibit this cortical area and to get rid of the focus. So, okay, so we know that there is a focus. And let us actually try to use ICA to get rid of the focus. I mean that to subtract it from EEG, because you know the focus actually it's disrupt the EEG spectra, and in the area of T4 you will see some changes that are not that are related with the spike with these spikes. So let us apply again ICA. Okay, I restore the initial fragment. I go again. I go to analysis. I use artifact correction procedure, and I apply ICA again, and I wait a little bit. It takes time. Okay, so, and again, we see here the first, of course, eye blinks. Okay, eye blink. The lateral eye movement. So you see eye blink, lateral eye movements. We got rid of them. Fine. And you see this component. And recall the topography of the focus. And this is the topography of the focus. I can show it to you. I just find the spikes. Wait. Okay, so this is a spike. Okay. Now, if I click, I discard, subtract this component from EEG. I click this topography. You see, spike disappears. So now we have EEG that doesn't have any signs of this spike activity. Okay. So EEG without max of eye blinks, artifacts of lateral eye movement, and the spike slow wave complexity, a clear EEG waveforms. Beautiful. Now you see that sometimes you see that there are some clear artifacts which probably associated with eye movement artifact. And we can get rid of this artifact using the other procedure, go to analysis and mark artifact. And we are going to mark artifacts which say excess of voltage. The voltage exceeds 100 microvolts, slow wave exceeds 50 microvolts, and the fast wave exceeds amplitude of 35 microvolts. Run, and this fragment will be marked as an artifact. And we are not going to use this EEG fragment for artifact for computing EEG spectrum. Now we are going to go to analysis, and we are computing EEG spectra. And this is the parameters of computation EEG spectra. So the epoch length is 4 seconds. The overlapping is 50%. The time window, we're using Hanning time window. And we are, of course, computing coherence. Okay, and click OK. So these are EEG spectra that we computed. Now they are free of any artifacts. And now we are going to compare them with the database. Compare with the database. This is EEG spectra. Load from the database, eyes open condition. And here we see the difference. And at the bottom of each, this is the difference. So EEG spectra in this particular subject minus EEG spectra computed for a large group of healthy subjects. And in this age group, the number of healthy subjects is 49. So the number that we are comparing this particular subject is 49 healthy subjects. And quite clear, and these are p-value or z-scores of the difference, or huge difference, deviation from the reference. And we can actually map this two deviation. One is at the T5 electrodes, and the other one, and the frequency here, the frequency is 4.15 hertz. And this is the other theta wave. The frequency is 3.6 hertz. And it looked like that quite clear there are two actually oscillation at theta frequency band. One is on the left side, the other on the right side. But to make sure that this is a correct assumption, we go back to the EEG that we already corrected the eye blink, lateral eye movement, and the focus. Let us do the next stop. Go to analysis and compute independent components. So we try to apply ICA to this fragment. And because we already corrected for quite many EEG fragments, the number of components, I think that 5 would be more than enough. And I apply ICA to this fragment, and these are, you can see here. Let me let me do this. So the x-axis is 20 hertz, and you can see these two components. One component is actually a component generated on the right side, the other component generated on the left side. The first component, the frequency, or the peak frequency is 3.6 hertz, and for this component, the frequency is actually 4.15 hertz. And of course, we can actually do Loretta and S-Loretta imaging. By the way, there are many types of finding the inverse problem. So you can do many types of solving the inverse problem. We are doing Loretta and S-Loretta because Roberto Pasquale-Marti is a good friend of mine. A long time ago, we decided to implement his software in our software. So by clicking one button, you can easily compute Loretta image. Let's compute Loretta image for this right frontal component. And I can use the as Loretta, standardized Loretta. As you can see, standardized Loretta shows you these fusiform gyros on the right side. And remember, theta activity in EEG on this age is actually indicator of severe idling of this part of the cortex, and the right hemisphere is responsible for emotion. And fusiform gyrus is the area which actually is responsible for recognition of faces. This could be a critical area for neurofeedback or for transcranial direct current stimulation. And let us look at the area on the left side. Let us do it. Also, Loretta for this component. Loretta for this component. And using standardized Loretta. Okay, so this is the area which is, according to what I see here, is Brodmann area 39, temporal, superior temporal gyrus. And it also can be associated with some symptoms of autistic spectrum disorder. Recall that the ventral stream is impaired in this disease. And you can do either neurofeedback, so you can, according to this, to this topography, you can say, for example, here you can place one electrode at T5 area. I just make it. Okay, so you see that you can put T5 if you want to activate this area, this superior temporal area. So you have to place one electrode at T5, the other could be, say, at O2 or T6, and to inhibit this alpha rhythm. I can demonstrate it here. So you can go to view, select montage, and then just try to implement the montage I just suggested, T5 on the left side and T6 on the right side. And this is going the EEG recorded in this particular subject, in this particular montage. And if you want to compute the EEG spectra for this montage, you just go to EEG spectra, you compute the EEG spectra, and you see, and that's what you have, T5, T6 electrodes montage. And this, what the EEG spectra would look like if you do this montage. In this case, if you want to do the neurofeedback, you have to suppress theta activity in the frequency band from 2.5 Hertz up to 5.5 Hertz. So that's what you are supposed to do with the neurofeedback. In our laboratory, we're using a transcranial direct current stimulation. In this case, I would use TDCS, transcranial direct current stimulation, in order to activate this cortical area. Well, anyway, I'm talking 1 hour, and it looked like that I need to stop somehow. Yeah.
Oh, this is all very interesting. Thank you very much. We do have a couple of very technical questions for you, if you can stay with us for a few more minutes.
Of course, of course.
One person asked, once the EEG is cleaned, can this now de-artifacted data be exported in EDF plus format? And
yeah.
I'm gonna add on to that, there is some concern in the community that once you apply ICA cleaning to data, that you're ruining the original. So Can
Of
you?
course, you are changing. You are changing original. You are not ruining. You are changing. You are getting rid of the artifact. That's what you are doing.
Okay, but do you do that in the file? So in other words, can you go back to the patient's
Of
original
course,
data?
of course, of course.
Okay.
Of course. The original data, it stays, and you know, in practice, you go back and forth. You do this type analysis, try to do, then you do the current source density, that look what is happening, then you go to event related potential to see what is there. So it's, you know, it's hard work. It's hard work, and is go back and forth. So you try this method, you try that method. And also you always start with the hypothesis. There must be initial hypothesis which you are going either to prove or to disprove. And this initial hypothesis is based on the previous research, not yours, of course, on your experience, but the research that was done in many laboratories. Just remember that the number of papers on ERP research is more than 2,000 ERP papers, and half of them are clinical ERP papers. Of course, the number of papers in QEEG research is 10 or even 100 times smaller, but still there is quite many papers on application quantitative EEG for diagnosis and for treatment different neurological and psychiatric conditions.
Okay. One person asked on the question of phase. Their point is that the distortion of phase is not within the EEG sample, but that if you apply ICA and then you join together several segments, that the issue with the phase calculation is really at the junction of segments. And then they go on to say that they assume that this is avoided if one calculates the ICA over a period of, say, 120 seconds of contiguous EEG. Could you comment a bit on whether or not the real issue with using ICA and its impact on phase is at the interface of segments rather than within segments, like your overlay demo?
That I can agree. That I can agree. But you basically mustn't do it. I mean that you cannot apply the ICA to this to the edges of this fragment, because of the edges of the fragment you have, you know, mixture different frequencies, and it could be not appropriate of using ICA for this fragments. You see that the EEG must be smooth.
So then someone asked the top limitations or concerns that should be considered. I'm hearing from you two then. One, we should really only use ICA to remove, well, stationary sources. So eye blinks and lateral eye movement are the only really correct artifact corrections application.
That is true. Yeah.
And then the second is that if we have a record that has many, say, electrode pops, such that we're going in and we're manually removing those, then we might be a little bit suspicious of phase, because we're going to be connecting those segments in the end analysis.
Yeah, you know, you can suggest many different situations in which the application of ICA does not work. That is true. But you know, I'm using this methodology for many patients. I'm helping many centers to use this methodology, and I quite rare see such cases in which the ICA is not appropriate. I understand that there can be some situation in which ICA is maybe you should use some other way, but we don't have a better way of analysis. Right now we have only PCA. It doesn't work in many situations, in many cases. EEG, ICA works much better, and yeah. But I agree that there could be some condition, there could be some EEG in which application of ICA is not suitable. That could be, you actually can suggest such situation. But in reality, it is not the case. And also, you know, that we used our database. Our database was made using ICA. So we apply the same methodology for spontaneous EEG on healthy subject. We also apply the same methodology when we correct eye blinks in patients. So we're doing the same methodological method in the same way. So basically, and it works in many cases. And also, you know, one thing, you're talking about coherence. We rely quite a lot in your research on coherence. We try to make sense of coherence, and we try to compare, you know, we have groups of patients with schizophrenia, 100 patient group. We have 100 patients with OCD. We have 1,000 ADHD subjects, etc., etc., etc. And we try to use coherence as a parameter for differentiating the groups. And we were not able to use this parameter. So coherence, at least in our database, cannot differentiate properly groups of patients with different psychiatric conditions. And that is why I'm not, when I do analysis, of course I compute EEG coherence, I can show EEG phase, but I'm not using this for clinical purposes. I can show you what EEG, what coherence look like in this case, and when you compare it with the database, but it doesn't tell you anything, unfortunately. So maybe my experience is quite limited, but this is my view.
People are also wondering then about EMG artifact and movement artifact. Mm-hmm. Would those be considered stationary such that you could use ICA to remove them?
Yeah, basically that is true. They are quite often they are stationary, and you can remove them. And but I would be very careful with this, because you know, in the database, when we built our initially database, we did not correct for muscle artifact. And when you do it, you of course you have to take into account that the component is linear combination of the potentials, and you actually can suppress some real activity in this particular electrodes. The image artifact, they're quite local, so you basically subtract one of the electrodes. So you have to be very careful when you compare with the normative database. Of course you can do it. Of course you can do it, and yeah. But you have to be very careful when you compare this EEG spectra with the database, because we didn't do it in the database.
Someone mentions that if they artifact EMG, it gives a flat outcome in that electrode. Yeah. And I think that's one overall concern with ICA, is that people that are new to it will select a number of components, and eventually you'll subtract out all your signal. Do you have any advice for how much do you go clicking on those components to remove them?
Yeah, it's a good question. Of course, you can actually suppress all activity. That's true. You have to be very careful. And my rule, I never touch imaging, never touch imaging, and I try to get rid of eye blinks all time, and very few lateral eye movements, very few. If I see that there are quite many of them, then I can do it. But basically, I don't do it. So you have to be very careful with application of ICA. Otherwise, you will get rid of all activity in the brain.
Someone asked if there are ways to generate group level ICA and analyze that. So for example, pre and post neurofeedback.
Yes, that's true. Easily, you can do it quite easy. So in our database, in our software, you can do it to group analysis. There is a special software for making group analysis. So you compute your own database, you compute the grand average age spectrum, grand average coherence, whatever, and you can compare easily by clicking one button. You can compare pre and post. It's not a problem. You know, the software that I showed to you, this is a software that we used for collecting our database. So basically, any one of you can use this software for collecting his or her database, using your own data. And the pre-post group analysis, easily, it's not a big deal.
If you, well, how would you compare artifacting using ICA versus the old school method of going in by hand and manually cutting out anything that the eye tells you is a source of artifact? Have you done side-by-sides, and how do those compare?
Yeah, we did it. We did it, and quite nice comparison. We even wrote a paper on this. Yeah.
Oh, that might be something I'll grab from you and see.
Yeah, although I think we probably have the translation in English, but it's initially it was in Russian. I can send you the English version of the paper. Yeah, we compared it. And there is a good comparison. So nothing against the old method. The old method are quite nice. You can do it, of course.
This just saves you a little bit of time, it sounds like, having to go through and to make those edits by hand, plus additional layers.
Yeah, that's very true. You know, ICA works just a few seconds and it's done, and you don't need to worry about this. And when I do analysis, I do it almost automatically.
And then it looks as if the last question here, I'm making sure that I got to everybody. Yes, it's possible to export the cleaned. We already went across that. We talked about the edge conditions, the junction of segments. We hit on a number of limitations, including muscle and movement. Can someone just starting out get a copy of this software just to kind of play with it and to, I think the intention is that they would like to do some hands-on exploration to learn by playing with it themselves. Is this available that they can download just to play with it?
Yeah, I think it's available. You know, the software actually is available through Mitsar company. So Mitsar company is the company, as you probably know, that is based in St. Petersburg, and they're making available this software. And in the US, we have Leslie Sherlin, who is actually a kind of distributor of this software. So if you write to Leslie Sherlin a letter and ask him to help you with the acquisition of this software, he will be able to help you, certainly. I don't know how technically it can be done, but or you can go to the web page of Mitsar company. Mitsar company, I think that for many years the software was free. I don't know if it's free now, but for many years it was free, so anyone can use it. But yeah.
I
Yeah,
suppose a EEG lab as well, if they just wanted to work with the mathematics of understanding signal decomposition, that might be another place, another learning opportunity.
yeah. The EEG lab is a very nice software, of course. And basically, I don't think that there is any difference between our software in terms of ICA and EEG lab software. I think it must be identical. I mean, we are using Infomax algorithm. This is the same that they're using in the EEG lab. Yeah. So basically, you're absolutely right. EEG lab and our software is identical. Must be identical. I mean, the results should be the same.
Well, that's good to know. And I hope that a lot of people will go and spend some time hands-on to further understand for themselves when they should be using it and when not to use it. For example, EMG, when should you use filters as opposed to, or cutting segments as opposed to using EMG? It sounds as if with a more sophisticated technique that end users, we simply need to understand the implication of the component removal decisions on the outcome. Yeah. And then we're on legitimate, good footing. I think we have, one more question came in just as I was finishing up. I think that people would like to, one person would like to know about whether or not there is further instruction on using the software. I think I will follow up with this person separately, as there are a couple of resources I'm aware of online,
yeah.
As well as additional training. So I'll finish up with an email to our participants doing that, as I see we're running over a little bit. And I would like to thank you for a wonderful talk explaining the theoretical basis of the technique. I appreciate seeing a demo. Oh, actually, one question from me. Loretta Explorer, where do I get this next level of the Loretta software?
I think at our webpage at the Key Institute.
Ah, okay.
I took this software from this webpage.
Okay, you know,
the Loretta and S-Loretta software I took just simply for this Key Institute webpage.
I'll jump back over there because I don't have their Explorer. I have sort of the base version. Okay, well, I believe that we're good here for now. Thank you very much. It must be late at night where you're at, and we appreciate that you've stayed up to share all this with us. Folks,
thank you. It's just only 8:20 and the sun is still in the sky. So it's not a real evening, it's just in the middle of the day.
So it's still before 11 p.m. your time then.
Yeah.
Well, ladies and gentlemen of our participants, our attendees today, just a reminder, you will get a copy of this talk probably on Tuesday. At that time, you'll be able to download your CEs from our granting organization. If you have any questions for Professor Kropotov, please email us and we'll be happy to forward those so that you're feeling like you're confident in the knowledge that you've learned here today. And then lastly, before we go, a reminder that our annual ISNR's annual meeting is coming up at the end of July. And take a look online to learn a little bit more about how we're doing it in a COVID world. It's going to be online, but we are going to have a really great lineup of speakers. So please continue to watch your email for any sort of updates as that speaker list becomes finalized. That's all from me today. And thank you all participants and our guest panelists. We'll see you again in a couple of weeks. Be safe, everyone.
Okay, thank you very much. Thank you very much all. And special thanks for ISINA organizers. Thank you.
Welcome, sir. Have a great weekend.
You too. Bye.